astronomers may have found a new type of object in the Orion Nebula. Serpens is a famous stellar nursery. What if I told you that the James Webb Telescope just found something in space that shouldn't exist? And not just one or two, but multiple structures like that. 6 massive galaxies were recently discovered by NASA using data released from the James Webb Space Telescope. Scientists are confused because they might just need to rewrite the textbooks. Let's take a look at what they have discovered. Number 1. Massive ancient galaxies. Massive ancient galaxies in an otherwise ordinary background. 6 bright red spots of light were discovered by the James Webb Telescope, and these are no ordinary spots. They are actually some of the earliest and largest galaxies ever found, dating back up to 13.3 billion years. These 6 spots were so red that they must have formed just a few 100 million years after the Big Bang. From what scientists previously believed, these structures couldn't even have formed back then. Experts used to think it took a lot longer for the first stars and galaxies to form, but in reality, these ancient galaxies were already massive and bustling with star formation just a few 100 million years after the Big Bang. One of these universe-breaker galaxies is 1 trillion times more massive than our Sun and 10 times the size of the Milky Way. That's huge. In the long run, this discovery has somewhat disturbed everyone because the universe didn't begin like we thought it did, and the dark ages for the universe may not have been so dark after all. Number 2. New finds in exoplanet molecules. For some reason, astronomers have been obsessed with finding an exoplanet with life. Among many candidates, there's K218b, which has life. Why is that? For one, they found water vapor in its atmosphere. Quite recently, James Webb found carbon-bearing molecules like methane and carbon dioxide. So yes, K218b may have a hydrogen-rich atmosphere and water ocean, perfect conditions for life. Wait until I tell you that there was even a detection of the compound dimethyl sulfide as well. Guess who produces that on Earth? Just living organisms. I'm sure you're smart enough to connect the dots here. Number 3. Origins of the cosmic web. Astronomers using NASA's James Webb Space Telescope also spotted 10 galaxies arranged like a string just 830 million years after the Big Bang. That's like finding a childhood picture of this universe. But why is it a big deal? Because these galaxies couldn't even have existed back then from our current understanding. Yeah, it looks like it was pretty inaccurate, wasn't it? Also, this structure is about 3 million light-years long and is anchored by a superbright quasar, which is a galaxy with a giant black hole at its center. And guess what? This line of galaxies might grow into a huge cluster of galaxies like the Coma cluster we know in our neighborhood in the universe. Number 4. Early supermassive black holes. You probably know that black holes actually grow in size by consuming passing stars and clouds of gas and dust. Thanks to James Webb, scientists have now captured supermassive black holes working in the early universe, even when they haven't had much time to feast on their surroundings. In fact, it also captured the most distant black hole ever seen in X-rays in a galaxy called UHD-1. The mind-blowing part? UHD-1 is a solid 13.2 billion light-years from Earth, meaning we're watching the black hole as it existed just 470 million years after the Big Bang. This black hole has an estimated mass between 10 million and 100 million times the mass of the Sun, which is downright unbelievable when you consider that it's comparable to the total mass of all the stars in its host galaxy. Number 5. HSE Head Nebula. This nebula is also known as Barnard 33 and is about 1,300 light-years away. All thanks to the instruments on the Webb telescope, astronomers have been able to see the small-scale structures of the illuminated edge of the HSE head for the very first time. It formed from a collapsing interstellar cloud and gets its glow from being illuminated by a nearby hot star. The gas clouds around the HSE head have mostly dispersed, but the iconic pillar shape is made of dense material that's hanging tough. Astronomers suspect that the HSE head has around 5 million years left before it starts to fade away. Now, astronomers can track how dust particles are being swept away from the cloud as they're evaporated by UV light and then create some really complicated patterns. Number 6. The dust left by a supernova. Then there's Copia A, the aftermath of a star explosion 11,000 light-years away, which happened around 3,140 years ago in the Copia constellation. We can still see its remains today. Astronomers are particularly transfixed by the warm dust, which plays a huge role in forming planets and life. Most of this kind of dust is believed to come from the heavy elements thrown out by supernovae. Because of James Webb, we can now see the tiny fragments of this debris made up of sulfur, oxygen, argon, and neon, all glowing in beautiful orange and light pink hues. The dark gaps you see in the image are caused by those tiny fragments piercing through the gas, leaving a cosmic trail of bullet holes. As if that's not amazing enough, we can even see light echoes, where the original light of the supernova gets absorbed and reprocessed as infrared light by the space stuff around it. Number 7. A star-forming region in the Serpens Nebula. Thousands of miles away, there's the Serpens Nebula, which is about 1,300 light-years from Earth. This area, which covers about 16 trillion miles by 11 trillion miles, is where many young stars are taking their first breaths. NASA's James Webb Space Telescope found many unusual things in this nebula. All thanks to it, they found aligned protostellar outflows, basically jets of gas expelled by newborn stars interacting with the surrounding gas and dust. These outflows are all aligned in the same direction, which has never been seen before. Not to mention, it also brought forward the Bat Shadow, a planet-forming disk that looks like it's flapping. Impressive, isn't it? Number 8. Unseen features in the Milky Way's heart. Not just that, we're getting a lot more information about our galaxy's dense center, all thanks to the James Webb Space Telescope. The telescope's near-infrared camera recently captured the most detailed image of the Sagittarius A* region, which is around 300 light-years from the Milky Way's central supermassive black hole. In this image, we can see like 500,000 stars, so it's no surprise that some truly mysterious structures have left astronomers scratching their heads. I'm talking about some needle-like structures in ionized hydrogen that seem to defy all known patterns and are much bigger than the scientific community initially thought them to be. And that's not all. A cluster of protostars, stars that are still in the process of forming and gaining mass, was also spotted. Number 9. Jumbo planets. If you're into space, I'm sure you've heard of jumbos. No, not the sandwich. I'm talking about Jupiter mass binary objects. They're these wild, free-floating planetary mass binary systems in the Orion Nebula, about 1,350 light-years away from us. James Webb found around 40 of these jumbos, and they're like nothing we've ever seen before. Each one has two parts, kind of like a double planet situation, with masses ranging from 0.6 to 14 times that of Jupiter. They're not tied to any stars. They're just out there on their own. Astronomers used a super-powerful telescope called the Carl G. Jansky Very Large Array to pick up radio waves coming from one of these jumbo systems called Jumbo 24. The radio signals are steady and come from both parts of the binary, and it's honestly quite shocking because these jumbos shouldn't be able to form or stay together as binary systems. Number 10. Analyzing star formation in depth. Scientists have always been curious about star formation, but stars form in dense clouds of gas and dust, right? Well, usually, dust blocks most of the visible light, so we can't see much. But that's where James Webb comes in. Its infrared radiation cuts through that dust and lets us see into all the never-seen-before details. Particularly speaking, there's the Rucci complex, which is only 390 light-years away from us. The telescope captured a frozen-in-time explosion featuring around 50 young stars, many of them about the same mass as our Sun. If it wasn't for James Webb, you'd be as good as seeing a black image. But what blows my mind the most is that the telescope's images have also captured dozens of young low-mass stars along with the high-speed streams of gas and particles they emit, lighting up surrounding clouds of molecular hydrogen. Number 11. Circles of the Ring Nebula. Then there's the Ring Nebula, also known as M57 in the Lyra constellation. We all know it's one of the coolest planetary nebulae out there, and it's not too far from us, only about 2,500 light-years away. But the James Webb Telescope has truly blown everyone's minds by revealing some awesome details about this nebula. The ring itself is made up of about 20,000 clumps of molecular hydrogen, and the inner region is filled with superhot gas. The main shell has this thin ring of carbon-based molecules called polycyclic aromatic hydrocarbons. That's a mouthful, but it just means that there's a ring of enhanced emission from these molecules in there. What sets M57 apart in the images are these 10 concentric arcs beyond the main ring. Astronomers think these arcs were formed near the end of the nebula's life cycle. In the future, M57 will get even brighter and puff up until it disperses completely, leaving behind only a faint, dim white dwarf star in the middle. Number 12. Probing the atmospheres of exoplanets. James Webb has provided unprecedented insights into the atmospheres of exoplanets. One remarkable example is the analysis of the atmosphere of WASP 39b, a hot Saturn-like exoplanet located about 700 light-years away. The JWST has revealed the presence of a range of molecules, including carbon dioxide, water vapor, and even sulfur dioxide, a compound that was previously undetected in exoplanet atmospheres. The sulfur dioxide detection suggests complex atmospheric chemistry that might be driven by high-energy processes. This discovery is crucial because it enhances our understanding of the atmospheric composition of exoplanets and could potentially hint at the climatic conditions on these distant worlds. Number 13. Reconstructing early galaxies. JWST has also shed light on the formation of early galaxies by examining their structures. In particular, the telescope has observed the distant galaxy known as HD1, which dates back to only 330 million years after the Big Bang. This galaxy is noteworthy due to its high rate of star formation and a mysterious population of massive stars. Researchers are intrigued by HD1 because its properties challenge our models of galaxy formation, suggesting that the early universe was more dynamic and complex than previously thought. These findings provide critical insights into how galaxies like our own Milky Way might have evolved over billions of years. Number 14. The complexities of stellar nurseries. Stellar nurseries, regions where new stars are born, have been extensively studied by JWST. One fascinating case is the region surrounding the massive star-forming complex NGC 2264, often referred to as the Cone Nebula. The JWST's detailed infrared observations have revealed intricate structures within this nebula, including detailed views of young protostars and their surrounding disks. These observations have provided a clearer picture of how stars interact with their environment and how the surrounding gas and dust influence star formation. The complexity and variety of these structures help astronomers understand the diverse processes involved in star birth. Number 15. The puzzle of cosmic dust. JWST has also tackled the puzzle of cosmic dust, which plays a critical role in the formation of stars and planets. One of the notable findings is the observation of dust in the galaxy GNZ11, one of the most distant galaxies observed by the telescope. The discovery of dust in such an early galaxy challenges previous assumptions that dust only formed in later epochs. This finding suggests that the processes responsible for dust creation and distribution were active much earlier in cosmic history than previously believed. Understanding the origins and distribution of cosmic dust is essential for comprehending the evolution of galaxies and the formation of planetary systems. Number 16. Observing the birth of stars in the Orion Nebula. The Orion Nebula, one of the most studied stellar nurseries, has been examined in new detail by JWST. The telescope's observations have revealed finer details of the star-forming processes within this nebula, including the detection of new, previously unseen protostellar jets and outflows. These high-resolution images provide insights into how young stars influence their surroundings and how they interact with the surrounding gas and dust. The observations also highlight the role of magnetic fields and turbulence in shaping star formation within this region. Number 17. The dynamics of black hole accretion. JWST has provided new insights into the dynamics of black hole accretion, the process by which black holes grow by pulling in surrounding matter. Observations of the quasar J0313-1806, one of the most distant quasars known, have revealed detailed structures in the accretion disk surrounding its supermassive black hole. These observations offer a glimpse into the early growth phases of black holes and their role in galaxy formation. The data also help scientists understand the feedback mechanisms by which black holes influence their host galaxies, impacting their growth and evolution. Number 18. The evolution of spiral galaxies. JWST's observations have also provided new information about the evolution of spiral galaxies. One notable example is the study of a distant spiral galaxy known as M100, which has been observed in unprecedented detail. The telescope has revealed intricate features of the galaxy's spiral arms and its central bulge, offering insights into how spiral structures develop and evolve over time. These observations are crucial for understanding the formation and growth of spiral galaxies, which are among the most common galaxy types in the universe. Number 19. The discovery of new Kuiper belt objects. While JWST is primarily focused on distant celestial phenomena, it has also contributed to our understanding of objects within our own solar system. Recent observations have identified new Kuiper belt objects, KBOs, including some with unusual orbits and compositions. These discoveries enhance our knowledge of the outer reaches of the solar system and provide clues about the early conditions of the solar nebula from which our solar system formed. Studying KBOs helps scientists understand the composition and dynamics of the outer solar system. Number 20. The structure of galaxies in the early universe. JWST has also explored the structure of galaxies in the early universe, providing new insights into their formation and evolution. Observations of the galaxy called SMACS J0723.3-7327 have revealed complex structures and interactions among its constituent galaxies. The detailed images show how these early galaxies merged and formed larger structures, offering a glimpse into the processes that shaped the universe's large-scale structure. These findings help astronomers refine models of galaxy formation and the growth of cosmic structures. Number 21. The hidden structures in the Magellanic Clouds. The Magellanic Clouds, two irregular galaxies near the Milky Way, have been studied in greater detail by JWST. The telescope's infrared observations have revealed hidden structures within these galaxies, including regions of intense star formation and complex interactions between the clouds. These observations provide new insights into the processes driving star formation in irregular galaxies and help scientists understand the role of galactic interactions in shaping the evolution of these nearby systems. Number 22. The search for life in icy moons. JWST's capabilities have also been extended to studying icy moons in our solar system, such as Europa and Enceladus. The telescope's observations have focused on the surface and subsurface features of these moons, seeking signs of potential habitability. Data from JWST will contribute to our understanding of the conditions on these moons and the possibility of life existing in their subsurface oceans. This research is part of a broader effort to explore the habitability of celestial bodies within our own solar system. Number 23. The interplay of galaxies and dark matter. JWST's observations have also contributed to our understanding of the interplay between galaxies and dark matter. By studying the distribution of dark matter in galaxy clusters and comparing it with the visible matter, scientists are gaining insights into the nature of dark matter and its role in shaping cosmic structures. This research is crucial for understanding the fundamental properties of dark matter and its impact on the formation and evolution of galaxies. Number 24. The formation of planetary systems. Finally, JWST has provided new perspectives on the formation of planetary systems. Observations of protoplanetary disks around young stars have revealed detailed structures and processes involved in planet formation. The telescope's infrared capabilities allow scientists to study the composition and dynamics of these disks, providing valuable information about how planets and planetary systems form and evolve. This research enhances our understanding of the origins of planetary systems, including our own.